we will give the explanation of anomalous Zeeman effect or the results of anomalous Zeeman effect on the basis of quantum mechanical theory. Okay, so for that, let us see how the results in anomalous Zeeman effects are obtained. We know the splitting of spectral line into a more than three components when placed in ordinary weak magnetic field is called anomalous Zeeman effect. Okay, and as we know, the splitting produced in an anomalous Zeeman effect is more complicated because it has more than three component lines. We cannot say the exact number of spectral lines produced whenever it is placed in weak magnetic field. Okay, again, it is to be noted here that the anomalous Zeeman effect is observed generally because it is frequently observed. As I have told you in the previous lectures, that the happening of anomalous Zeeman effect is general. The anomalous Zeeman effect is called so because it does not find its explanation on the basis of simple classical theory. By using the simple classical theory, we cannot give the theoretical explanation of anomalous Zeeman effect, though it is generally happened. Okay, so now today we have to prove, or we have to explain the results of anomalous Zeeman effect using the quantum mechanical theory. Okay, for that, let us consider the spin as well as orbital motion. Spin as well as orbital motion. So to explain the anomalous Zeeman effect quantum mechanically, we have to take into account the orbital and spin motion of electrons. Okay, here so for that, the total angular momentum of an electron will be J equal to, in place of negative sign, actually there is a equal to, should be there. Okay, so the total angular momentum of an electron having spin and orbital motion is equal to L plus S. That is our equation number 1. Okay, so as we have considered both the motions for electron, the orbital angular momentum of an electron will be L, capital L, that refers to the total angular momentum, which is equal to under root of small l into L plus 1 out of the under root sign H cross is there, where L is the small l will be orbital quantum number or azimuthal quantum number. Okay, so from the orbital angular momentum, we have, or we can calculate the value of total or the orbital magnetic moment mu L, which is equals to E by twice m times capital L. As I have told you in the previous lecture that the magnetic moment equals to electromechanical ratio times orbital angular momentum. Okay, so it is about the orbital moment angular momentum denoted by mu L. Here L is used because to represent the orbital motion. Similarly, the spin angular momentum can be calculated for the electron as capital S equals to under root of S small s into small s plus 1 out of the bracket, out of the under root sign H cross. Okay, again from capital S we can calculate the spin magnetic moment. Okay, it is denoted by mu S equals to here 2 times, here the sign 2 or the number 2 is put because the electrons spin motion have two kinds, or there are two kinds of the spin motions are possible, whereas the orbital motion is having a single direction. Okay, therefore for clockwise and anti-clockwise spin, two kinds of the spin motions, we have put the sign or number 2 here. Therefore the spin magnetic moment will be 2 into E by twice m times capital S, that is spin angular momentum. Okay, so it is about the spin magnetic moment and orbital magnetic moment of an electrons denoted by equations 1 and sorry 2 and 3. Okay, now Let us move towards the further possibilities that because of the negative charge of an electron, the directions of mu l and mu s are in opposite to that of vectors l and s. Let us see here, it is a vector l. Just see the vector l. So here vector l is opposite to the its magnetic moment, that is mu l. Okay, the arrows are in opposite direction. See both the arrows. Okay, also the vector s is having upward direction, and its magnetic moment mu s is having opposite direction, that is in a downward direction. Okay, it is happened because of the negative charge of electron. Then, by considering orbital as well as spin motion of an electron, we can calculate the resultant magnetic moment in an atom for the single electron will be mu equals to mu L plus mu S. Here S plus sign denotes not a simple sum, but it's a vector sum of mu L and mu S. Okay. Now, in presence of the magnetic field, the vectors mu L and mu S, that is spin and orbital magnetic moments, presage about the vector J. Here, as we have discussed earlier, that this precessional motion is the motion on the surface of cone. Okay, conical motion on the surface of cone. So in presence of magnetic field, the total angular momentum or the total quantum number J precedes about the direction of magnetic field. Similarly, the vectors mu L and mu S also precedes about vector J. During the precessional motion, what happens? Let us see here. Whenever we considered spin magnetic moment as a mu s and orbital magnetic moment as mu l, then from the vectors law we can calculate the resultant magnetic moment mu as vector law of triangle law of the vector addition. Okay, therefore here mu denotes the resultant magnetic moment by considering its all components. Okay, but during the precessional motion, what happens? The effect of perpendicular components of mu, that is perpendicular components of resultant magnetic moment, vanishes. Here see, this dotted line indicates the direction of perpendicular components. So what happens? During its precessional motion, the perpendicular component on one direction vanishes or cancels the perpendicular component on other direction. Okay, because during its precessional motion the vector rotates about its axis. Hence the resultant magnetic moment will be only due to the resultant magnetic moment of parallel components only. Okay, therefore the effective value of resultant magnetic moment will be mu j in place of the mu. So we can write here mu j as a effective value of resultant magnetic moment of mu l and mu s by considering its precessional motion about vector j. Okay, therefore the above equation, that is mu equals to mu l plus mu s, can be written as mu bar equals to mu j bar. Here mu j refers to the resultant by considering parallel components of mu only. Okay, therefore mu j equals to mu l bar plus mu s bar. That is our equation number 4. Okay, now for the further calculations we can use the resultant magnetic moment as a mu j, or mu equals to mu l bar plus mu s bar. Okay, So it is about the resultant magnetic moment. Now we have to calculate the magnitude of mu j along j. Okay, because if we consider in place of the mu j, whenever we consider the mu as a resultant magnetic moment, then it can be obtained by just vector sum of mu l and mu s. Okay, but among the mu we have left the perpendicular components. Therefore we need to calculate the value of mu j separately by using some other type of calculations. Okay, therefore the magnitude of mu j along j means, see in the figure here, the vector j is shown at an which is inclined to direction of magnetic field. Here on other direction of j, the mu j is there. Okay, that means direction of mu j and j are just opposite to each other. Therefore I have mentioned here the magnitude of mu j along j. Okay, which is equals to mu l into cos of lj. Here cos of, or the in bracket l comma j, represents the angle between l and j. Okay, plus mu s into cos of sj. Here in bracket sj represents the angle between vectors capital S and capital J. Okay, the angle made by vector L with vector J and angle made by vector S with vector J. Okay, these angles can be calculated from the cosine law, cosine cosine law of the vector addition. So from cosine law, we can write cos of Lj equals to vector L square plus j square minus s square divided by 2Lj. Okay. Similarly, cos of Sj can be written as cos of Sj equal to s square plus j square minus L square divided by twice Sj. Okay. It is our equation number 6. From equation 6, we can, or we have calculated the values of angles between Lj and Sj. Now put these values of cos of Lj and cos of Sj in equation number 5. Again put the values of mu L and mu S from equations 2 and 3. Therefore the equation 5 will be mu j equal to E by twice m into L, that is our value of mu L. Okay, into cos of Lj equal to L square plus j square minus s square divided by twice Lj plus 2 times E by 2m into s, that is our value of spin magnetic moment from equation 3, into cos of Sj equal to s square plus j square minus L square upon twice Sj. Okay, so let us simplify this equation. So I have written the same equation as it is. Again take E by twice m common from both the terms. The remaining part will be here. L on numerator and denominator of first term cancels each other. Again capital S from numerator and denominator from second term cancels. Therefore the remaining terms will be, we take E by twice m as a common. So remaining terms will be L square plus j square minus s square upon twice j. Here L got cancelled. Okay, plus here the remaining 2 and doing 2 in the denominator also cancels. Here 2 from numerator and 2 from this denominator also cancel. S also got cancelled. Here L cancels from denominator. Okay, so here only j is remaining in the denominator. So the second term will be plus s square plus j square minus L square upon capital J. Okay, now cross multiply by these two equations. So here first term will be cross multiply by this j to the first term, that is the equations become j into l square plus j square into j minus j into s square. Okay, every time here j is there. Okay, in the second term multiply by this twice j to the second term. Okay, here therefore twice s square j will be there plus twice j square into j minus twice l square into j. Okay, from all the terms we have taken the j common, written I have written here directly. Therefore our equation will be ej upon twice m in bracket l square plus j square minus s square plus here 2 is multiplied to every term. Therefore, plus twice s square plus twice j square minus twice l square divided by cross or multiplication of twice j and j, that is twice j square. Okay. So again here plus l square minus twice l square, that is minus l square will be there. Okay. So j square plus 2j square, that is our 3j square, 2j square plus j square, that is 3j square. Okay, here 3j square will be, okay, again minus s square plus 2s square, that is s square. Okay, here s square will be remaining, means the equation remains will be 3j square plus s square minus l square upon 2j square. Okay, among the 3j square I have written here 2j square. Just remember here 2j square plus j square only. 2j square plus j square direct, that means here only j square is remained plus s square minus l square upon twice j square. Here we have separated the denominator, therefore our equation will be, we can write this equation as 2j square divided by 2j square. Okay, 2j square divided by 2j square plus j square plus s square minus l square upon 2j square. Okay, these 2j square from numerator and 2j square from denominator cancel each other, therefore only one is remains here. Okay, therefore our equation for mu j will be mu j equal to E into capital J upon twice m in bracket 1 plus j square plus s square minus l square upon 2j square. Okay. Now put the values of capital L, that is orbital angular momentum, spin angular momentum and total angular momentum capital J in above equation. Therefore we can write here E upon twice m as it is, in place of the capital J write under root of small j into j plus 1 into h cross. Okay, the equation will be E h cross upon twice m under root of j into j plus 1 in bracket 1 as it is, in place of j square we have written here square and the square root cancel, therefore the term will be j in bracket j plus 1 into h cross square. Here h cross square is there in the first term. Again in place of s square write s into s plus 1 h cross square minus in place of l square put here small l in bracket l plus 1 into h cross square. Okay, so from all the three terms take h cross square common. Okay, again in the denominator there are 2j square, means 2 into j small j in bracket j plus 1 into h cross square into h cross square. This h cross square from numerator and denominator cancel, therefore the equation which is remains will be mu j equals to eh cross upon 2m in bracket under root of j plus 1 in bracket 1 plus j into j plus 1 plus small s into s plus 1 plus minus small l into l plus 1 divided by 2 small j into j plus 1. Okay, so the value of this bracket will be small g, that is called Landau splitting factor. Okay, so in place of the this bracket we can put here small g. The equation simplifies to the form mu j equal to E h cross upon twice m under root of small j in bracket j plus 1 into small g. So g will be equal to plus 1 plus j into j plus 1 plus small s into s plus 1 minus small l into l plus 1 divided by twice j plus 1. Okay, it is the equation number 8, and it is called Landau splitting factor. Okay, and this factor determines a kind of splitting of spectral line in presence of or under the application of weak magnetic field. Okay, so the equation will be E h cross upon twice m under root of small j in bracket j plus 1 into g. But E h cross upon twice m is known as Bohr magneton. We have used this expression in the previous article, that E h cross upon twice m is called Bohr magneton, denoted by mu b, and it is a smallest unit for measuring the magnetic moment of an atom. Though its orbital magnetic moment or spin magnetic moment, it can be measured in the units of Bohr magneton. That means we can say that for a particular atom, the Bohr magneton is 5 times, or the 5 Bohr magneton, 6 Bohr magneton, or so on. It is measured in the units of Bohr magneton. Okay, E h cross upon twice m, it is a constant quantity. 9.27 into 10 to the power minus 27 is the value of Bohr magneton. Okay, so after substituting the value of Bohr magneton, the value of mu j will be equals to under root of small j in bracket j plus 1 into mu b into g. That is our equation number 9. Okay, so up till we have calculated the value of effective resultant magnetic moment of an atom by considering its orbital as well as spin motion. Okay, now we know under the application of magnetic field, the vectors capital L and capital S presages about the direction of magnetic field that gives the additional energy to electron. This calculation is somewhat similar to the previous calculations we have, as we have discussed in the explanation of normal Zeeman effect. But in place of here capital L and S are used. Okay, so L and S gives additional energy to the total angular momentum of atom, that is for the capital J, and this additional energy achieved by electron is called the interaction energy. Okay, and this value of interaction energy is responsible for splitting of a single line into various components. Okay, the value of this interaction energy delta E equal to mu j bar dot b bar, which is equal to mu L into B in a previous article. Okay, so we use the vectors rule, that is A bar dot B bar equal to AB cos theta. So here interaction energy will be mu J B cos theta, where theta is the angle between mu J and B. Here in the figure I have shown this angle as angle between B and J, but we know the vector mu j is along j, therefore it will be angle between mu j and b. Okay, so from the figure we can calculate cos theta. Cos theta equal to adjacent side, that is mj into h cross divided by hypotenuse, that is capital J. So cos theta will be equal to mu j into h cross upon, in place of capital J we have substituted under root of small j into j plus 1 h cross. Here h cross on numerator and denominator cancels. Therefore cos theta will be equal to m j in place of L. There should be small j. Okay, small j should be there. So mj upon in under square bracket or square root small j into j plus 1. Now put this value of cos theta in equation number 10. Therefore, the interaction energy will be mu j into b into mj upon under root of j into j plus 1. Okay, under root of j into j plus 1. Here j should be there, small j. I have corrected in the next term. Okay, therefore delta E will be equal to mu b into g, mu b into g into under root of j into j plus 1. I have taken this value or first term from the value of mu j from equation number 9. Let's see the equation number 9. Equation 9 gives you the value of mu j equal to under root of j plus 1 into mu b into g. Okay, into capital B from the equation 10 as it is. In place of cos theta, we have substituted mj upon under root of j plus 1. This square root from numerator and denominator cancels. Equation will be delta E equal to E h cross upon twice m into g into b into mj. Okay, into mj. Okay, here we know EH cross upon twice M is called, or in place of this H cross, just take here B in front and keep the H cross next to B. Therefore, equation will be EB delta E equals to E into capital B divided by twice M. Okay, into G as it is into H cross here into mj. Okay, but we know the angular velocity of electrons omega L equal to eb upon twice m. Okay, just put this in place of the term eb upon twice m in above equation. Therefore the interaction energy will be omega L into capital G into H cross into mg. Okay, just put here mg. Okay, so also omega L, that is the angular velocity, can be written as twice pi nu L, twice pi nu L, because we know omega equal to 2 pi by T or twice pi nu. So omega L will be equal to twice pi into nu L into G as it is. In place of H cross, I have put here H upon twice pi into mj as it is. Okay, mj. So twice pi from this numerator and denominator cancel. Therefore, the equation for interaction energy will be H into nu L, H into nu L into G into mj. That is our equation number 12. Okay, so here the interaction energy, or it may be called the separation between energy levels, is delta E equal to H nu L into G. Okay, because the values of mj are ranging from minus j to plus j including 0. Okay, these are depends upon the transition between, or the energy levels available for transitions. Okay, whereas this difference or separation between energy levels in case of normal Zeeman effect, that will be h nu. Okay, here the factor g is there, and as we have defined the g as a Landau splitting factor, that will explains the complex splitting of spectral lines in presence of ordinary weak magnetic field. Okay, therefore in anomalous Zeeman effect, more complex splitting is obtained, which is shown by or explained by the Landis splitting factor. Okay, so in this case, there is no necessary of showing the energy level diagram because the splitting is much complicated or much complex. Just see the splitting of spectral lines. In case of normal Zeeman effect, there are only three spectral lines are obtained, but in this case, more than three are the complex spectral lines. Complex splitting of the spectral line is obtained here. Okay, so it is about the today's topic. Thank you. You can ask me any difficulties if you have.